So let's consider these two functions here. F of x equals 2x plus 9, and g of x equals x minus 9 divided by 2. And we're going to calculate the following. So I see a composition of functions here, g of f of 15. So I'm going to start and figure out what the output of function f is when I plug in 15. And then I'm going to use that as an input to plug into function g. So 2 times 15 plus 9. 2 times 15 is 30, plus 9 is 39. So now I'm going to plug that in for g, right? So g of 39 is going to be 39 minus 9 divided by 2. And 39 minus 9 is 30, divided by 2 is 15. I'll try that again for b. I'll plug in negative 3 for f into x, right here and here, and then I'll do the same thing for g. So f of negative 3 is 2 times negative 3 plus 9. And if you simplify a little bit, 2 times negative 3 is negative 6, plus 9 is positive 3. So I'm going to plug that positive 3 into g for x. So 3 minus 9 divided by 2 is negative 6 over 2, which ends up being negative 3 again. So let's just do it one more time more generally. Rather than picking any particular input, I'm just going to plug in the whole function f of x, that 2x plus 9, in as an input for my x value. So for g of 2x plus 9, let's see what happens. So if I plug that in for x, it's going to be 2x plus 9, that's my substitution, minus 9 divided by 2. Well, it looks like I could do something to clean up in the numerator there. 9 minus 9 is just 0. So g of 2x plus 9 ends up being 2x divided by 2, which is just x, which was in fact my original input into f to begin with. As a matter of fact, my original input is the same as my final output for all of these. And the reason that is because g and f are actually inverse functions of one another, meaning that they undo each other. So what appears to be true when you compose these two functions? My input ends up being the same as my final output. And we're going to see that happens every time we compose inverse functions. So here's the big idea. Generally, if you think about a function, let's say we've got a domain right here, we've got a function f. A function takes some value in a domain, and it sends it to some value in a range. Well, the inverse of that function takes that corresponding y value, that range, and it sends it back to that value of the domain. So if I plug in a to my function f and get b, then when I plug in b to my function g, I should get a. Let's do a couple of examples with some numbers. So if the point negative 3, 5 lies on the graph of y equals f of x, which of the following points must lie on the graph of the inverse? Well, let's think about this point right here. My input is negative 3, and my function f is sending the negative 3 to the output of 5. And my inverse function should do the exact opposite. It should send my output of 5 back to negative 3. So that relationship would be if I plug in 5 to my inverse function, I should get back out negative 3 as an output. So 5, negative 3. Really what we're doing here is just swapping x and y. So that's a quick trick to figure out some points that could be on your inverse function. So normally, we write a function as y equals f of x, but we write the inverse when it's also a function, and we represent it as y equals f inverse of x. So it looks kind of like an exponent of negative 1, but it's just telling us that this is the inverse function. So again, I would read this as f inverse of x. Let's try a couple of examples. So let's say I've got this linear function right here, right? It's got a slope of 2/3 and it's got a y-intercept of negative 2. And it wants me to evaluate a couple of inputs and outputs for the inverse function. So let's just look at a couple points on this graph. I've got a y-intercept here at 0, -2. I've got an x-intercept here at 1, 2, 3, 0. And I've got that point over there. Let's see, what would that be? 1, 2, 3, 4, 5, 6, 2. That's just to look at a couple points, and maybe this one down here, which is -3, -4. And let me just make that a brighter color so we could see that. And let's take a look at these. So it's asking me to evaluate f inverse of 2, where that's an x value on my inverse graph. So I've got to look to my graph here and see where I have an output of 2. And I notice that this point right here, that's 6, 2, has an output of 2. So if 6, 2 is a point on f of x, the corresponding point on f inverse of x would have to be 2, 6. And the whole idea behind this is that we could swap the x and y values or swap the inputs and outputs. So if I were to plug in 2 to my inverse function, I should get out an output of 6. So to answer that question, f inverse of 2, that's just going to be 6. So for f inverse of 4, if that's going to be an input to my inverse function, it's really an output on f of x. So if I look to my function here that I have, I notice that this point down here, that -3, -4, has an output of -4. So the corresponding point on my inverse graph would be those points swapped, -4, -3. So when I plug in -4 to my inverse function, I get out -3. So f inverse evaluated at -4 is just -3. Now here's where it gets a little trickier. It says determine the y-intercept of f inverse of x. So let's think about that. If I have a y-intercept on my graph, that's going to have an x value of 0. So really what they're asking me here is, if I plug in 0 for x in my inverse function, what will be my output? So if this is the input for my inverse, I would need to look for a point on my graph where the output is 0. Because remember, you'd have to swap the x and y values. And I notice it's right there. So if let's say my x-intercept here is 3, that means my y-intercept on the corresponding inverse graph should also be 3. And let's convince ourselves that that's true, right? This would represent the point when I plug in 0 for x, I get 3 out for y on the inverse function. But if I look at my regular function here, when I plug in 3 for x, I get out 0 for y, which represents the point 3, 0. So it makes sense that my function, my original function, sends 3 to 0, and my inverse function does the exact opposite. It sends 0 to 3. That's going to be the case every time we have a function and an inverse function and we're looking at them graphically. Algebraically, it's a similar idea. So let's take a look at this. If f inverse of x is 2x plus 7, find f of x. Well, the process for finding f of x given the inverse is the same as if we're finding the inverse given f of x. We could still just swap the x and y values. So remember, f inverse of x, that's still showing you an output, so we could still call that a y value. So this is my inverse function. And in order to find the original function, we just need to swap our x and y values. Ooh, that orange does not look good there. Let's try blue. All right, that's a little better. So I'm going to swap x and y. X is equal to 2y plus 7. Now the only thing we need to do is just rearrange this so that we have y isolated. So I have 2y is equal to x minus 7, and I can divide out the 2 to get y equals x minus 7 over 2. So this is my inverse function here. So I'm going to replace y with f of x and call it a day. So algebraically, the way to go from either a function to find its inverse function, or to go from an inverse function to the original function is exactly what we did for the points where we swapped x and y. So we're just going to swap x and y. That's always going to be our first step. Maybe you could think of a step 0 as replacing the function notation with just a y equals. And then we're just going to rearrange the function to isolate y, and that's going to be either our function or our inverse function depending on what we're looking for. The only issue comes in is when we're dealing with some rational expressions or rational equations, it can get a little bit tougher to think about. Let's take a look at this function down here for number 4. 5x divided by 3x plus 1. And they're asking me to find the inverse. First thing I'm going to do is just replace that f of x with y, because remember those outputs, they just mean the same thing. And there becomes an issue here where I go to swap my x and y values. The problem is I've got x in 2 places, but the process still works. Everywhere I see a y, I'm going to write an x, and everywhere I see an x, I'm going to write a y. So that causes an issue when we're trying to isolate y, because now it's in 2 places. So I'm going to start just by multiplying both sides by 3y plus 1, because I don't like to deal with fractions, and I know if I multiply it, it would reduce over here to 0, and I'd be just left with 3y plus 1 times x is equal to 5y. I'm just going to distribute this x into the parentheses here to get 3xy plus x equals 5y. And my goal here is try to get all of my y terms together, because I have a y over here, and I have a y over here. And if I could somehow get those to the same side of the equation, maybe I could factor them out and get something going. So I'm going to subtract 3xy on both sides. It reduces to 0 here, and I just have x equals 5y minus 3xy. And now this was a pretty smart step to do, because I noticed that if I'm thinking about my factoring skills, 5y and minus 3xy have a y in common that I could factor out. So I'd be left with 5 minus 3x, still x on that side. Now before, in this step, it wasn't possible to isolate y, but now I only have one y, so it is possible to isolate that y. It's only linked to the 5 minus 3x by multiplication. And remember, the inverse operation of multiplication is division, so I'm just going to divide out that whole 5x minus 3. The reason why this works is because 5x minus 3 divided by 5x minus 3 reduces to 1. So really all I'm left with is just y equals x over 5 minus 3x. So this is my inverse function. F inverse of x is equal to x divided by 5 minus 3x. So again, we swapped x and y. That was the first step we did. We replaced f of x with y, and then we swapped x and y. And then we multiplied both sides by the denominator, so it wasn't a fraction anymore. And the goal was to get all of our y terms on the same side so that we could factor it out, that we did in this step, and divide out to get our y isolated. Let's try one more example. So if you think you have an idea of what we're doing here, I encourage you to stop this video right now, do it yourself, and then come back to see if you got the correct answer. I'm going to do the same thing. I'm going to change it to y equals, and then to find the inverse, I'm going to swap x and y. So instead of y equals, it's x equals, and there's a y minus 3 there instead of an x minus 3. So I'm going to try the same trick where I subtract 1, so I have x minus 1 equals y minus 3 cubed. So remember, the inverse to cubing something would be taking the cube root. So I'm going to take the cube root on both sides. If I take the cube root of something cubed, I just get whatever that something was, and there's nothing I could really do to simplify on this side. And then from here, this is just a one-step equation. I can add 3 on both sides, and I'm just going to rewrite it so that my y is on the left-hand side, to have the cube root of x minus 1 plus 3. Just be careful, I won't be able to add that 3 to the 1 because the 1's trapped under the cube root there. And lo and behold, I have isolated y. I started with a function, and now I have found the inverse to that function, which is just the cube root of x minus 1 plus 3. And that should make a little bit of sense because this function right here is something cubed, and part of my inverse is something cube rooted. And we already know that cube roots and cubing something are inverses of one another. So remember, we swap x and y and isolate y. The easiest thing to forget is to rewrite y as whatever they told us to find. So even if we have this equation right here, we're not showing that we found the inverse function. The inverse function should say f inverse of x. So in class on Monday, we're going to practice a lot of different types of these. So even if you feel like you only got 80% of this, make sure you have questions to ask in class on Monday.